Alright, so what we're doing here is we're looking at an example of using the critical values, critical points, which your book calls stationary points, but the more common term is the critical values, which give us critical points. And we're going to use this to actually come up with a sketch of this function, x cubed plus 5x squared minus 4x minus 20. Now, before we even get to the derivative portion, let's talk about what we would have done in the past if we were asked to sketch this. Because there are some features that we can identify even without using the derivative. Okay? Now, you'll notice here, with our function, we have a cubic. And what have we done in the past trying to sketch some of these functions? What would you do in the past?
Maybe look at the function, leading coefficient, and see like where it goes up and down and stuff.
Okay, good. This has an odd degree, it's a cubic, and we have a positive leading coefficient. So I know that the general trend is going to go from left to right, it's going to go up. Alright, so it's going to look something like this. Okay? Just like a line with a positive slope goes like this, a cubic with a positive leading coefficient is going to trend upward. Okay? What's something else that we can figure out? We could find roots, which will translate into the zeros of the function, right? Okay, so we can find zeros. How do we find zeros?
Synthetic position.
We could, what?
Equal to
Set the actual function equal to 0. X cubed plus 5x squared minus 4x minus 20. And this actually does factor if you do factoring by grouping. I'm going to group these first two terms and the last two terms together. And from the first two terms, they have a common factor of x squared. And there's an x plus 5 left over when I factor that out. My last two terms have a common factor of negative 4, which when I take it out, I end up with an x plus 5. So now I know that 0 equals, I have the binomial common factor of x plus 5 in these two terms, and then I have an x squared minus 4 left over. So I know that my zeros are at x equals negative 5. And what 2 do I get from the x squared minus 4?
2 and negative 2.
Good. Plus or minus 2. 2 or negative 2. Alright, good. Good. So we can get those features. We can also figure out our y-intercept. What's our y-intercept?
When x equals 0.
When x equals 0, so what? Negative 20. Okay? Our y-intercept is at y equals negative 20. Okay? Now, the challenge with these is the best we could do was a rough sketch that kind of approximated where the max and min values were. And sometimes we would like average the zeros, and that kind of gave us a ballpark idea of where the zeros or where the max or min points would be. Alright, so using the general trend, I know I was going up to this 0, and I would go up after here. I know that my y-intercept was down here at negative 20, but I don't know if that was actually the min point, but it's probably kind of close to the min point. So we just kind of would eyeball the rest of it, okay? And go like that. So that's going to be generally what our function looks like. However, what we're looking at in this section is now using the derivative to find what these critical points are, here and down here. What are those critical points? Okay? So I'm going to erase this right now so we have some room to work. And let's set this all to the side a little bit. We'll use that later when we go to sketch everything. But let's find the critical points. Now, where are the critical values? It's when the tangent equals 0, when the slope of the tangent line equals 0. So what we need to do is we need to set f prime of x equal to 0. And that will give us our critical values. Okay?
Wait, it would give all of them?
What?
It would give all of them or something?
It would give all of them, yes. Alright, so the derivative here, f prime of x, at this point, this is easy for you. You've got a 3x squared plus 10x minus 4. Now we need to set that equal to 0 in order to find our critical values. Alright, so it's a quadratic. You guys know how to solve quadratics. You could try to factor, but this one actually does not factor. So we would have to use the quadratic formula. So let's do that real quickly here. X equals negative 10 plus or minus the square root of 100 minus 4 times 3 times negative 4. So it's plus 48 all over 2a, so that's all over 6. Okay? And if we could have some help on the calculator, what's the square root of 148? Should be 12 point something, like 12.1 or...
We need to get these numbers.
12.1655.
Okay, 12.16, so we'll make it 12.2. What'd you ask?
We need to get these numbers.
The quadratic formula, negative b, b's 10,
B squared.
so negative
Oh,
10,
yeah.
b squared minus 4ac. Okay. Alright, so now, when we do a negative 10 plus 12.2, it's 2.2 over 6. What's 2.2 over 6?
0.36.
What?
0.366666.
Okay, so let's round that to 0.37. And then if we subtract the 12.2, we get a negative 22.2 over 6, which I think was 3.7. Is that right?
Negative 22.2?
Yeah. Divided by 6?
Yeah.
Okay. Alright, so that gives us our critical values.
And what's critical value?
That's where the max and min points are going to occur.
Yeah, to be
Oh.
negative.
Now, I'm not sure which one is a max, which one is a min, but let's tie this to what we were doing, okay?
This section should be the 3.7 negative.
Oh yeah, thank you. Negative 3.7, okay? So, this part we already did. Now, let's actually use that. We talked about a sign diagram, okay? The sign diagram, we're going to put our negative 3.7 here and our 0.37 here, and this will help us indicate which intervals our function is increasing or decreasing on. Okay? Now how do we do that? We're going to pick a value in each region. Okay? You don't have to get super creative, just pick the easiest one that it would be to evaluate. Alright, so I'm going to pick 0 here, and 1 here, and we'll go with the negative 4 here. And I'm going to plug that into what?
Original.
Derivative.
The derivative, because I want to tell, is our derivative, is our slope positive? Is it increasing? Or is our slope negative? Decreasing. Alright, so I'm going to do f prime of negative 4. Negative 4 squared is 16 times 3 is 48.
Isn't the slope 0?
Not at negative 4. Only is 0 at these two values here.
Why are you getting, why are you getting, what, I don't understand it.
Did you watch the video? That's why you don't have a clue. Alright? I gave you the video to watch. If you didn't watch it, you don't know what's going on. So you need to go back and that'll explain why we're doing this. Okay? I picked negative 4 because it's in this region. Alright? I plug it into this function. So that's 48 minus 40 minus 4. And really, the value itself doesn't matter. What matters is the sign. Okay? So that's 8 minus 4. That's a positive 4. Since my derivative is positive here, I know that my function is going to be increasing in that interval.
Because we get positive 4.
Because we got a positive slope for our tangent line. Okay? And if one of the points has a positive slope for the tangent line, then everything in that interval up to the critical value is going to have a positive slope. Alright? So I do the same thing with f prime of 0. That's negative 4. So I know that my function is going to be decreasing over that interval. Okay?
But what about the values between negative 3.7 and 0?
Well, this whole interval will behave the same way. From negative 3.7, my critical value, to my next critical value,
Decreasing?
all of those points will have a negative slope. Yes?
Don't you really just need to find the first one? If they're critical values, then won't it make that shape naturally?
Not necessarily, and that's where we have the plateau points. It's possible that we level off and then continue to go up. If you remember your parent function x cubed, it does that. There's a plateau point here.
So it could go back up. Okay.
Yeah. So that's why we look at this. If we were increasing and now we're decreasing, what does it mean? What kind of point is right here?
Max.
It's a max point. Alright? When you have a change from increasing to decreasing, that means that negative 3.7 is a max point. And then, if I do f prime of 1, I get 3 times 1 is 3, plus 10 times 1 is 10, minus 4, that's a positive 9. I'm back to increasing, so I now know what exists at 3.37.
Minimum.
A minimum point. Okay?
If our y-intercept is negative 20, but our minimum point of the function is
Yeah, that's
0.37,
why.
how does that work?
Well, our minimum isn't 0.37, it's at x equals 0.37.
Oh, probably
If-
y equals 20.
Yeah, remember, and let's actually start sketching what we know so far, and we'll actually find what those values are.
If we plug the 0.37 in, will we get negative 20?
We'll see.
We'll actually get something a little smaller than negative 20, because negative 20, I'm going to go by 2's on my y-axis.
Right.
Negative 20 would be right here. My minimum values is going to be at 0.37. Okay? So we had negative 2 as a 0 and positive 2 as a 0. And remember I said you can average the zeros to kind of get a ballpark idea of where your min will be. It's not exactly the minimum, but it's in the right area, okay?
Can you like save this exactly the way it is online?
So we have these. We know we're increasing on this interval. Let me stop drawing the arrows. Okay. It's increasing on this interval, and then we need to figure out how high it's going to go. We know it's going to reach its peak at negative 3.7. Okay? These are not asymptotes. I'm just showing you where my critical values are. Negative 3.7, I'm going to have a max, and at 0.37, you're going to have a min. Okay. What?
We just plug them in.
We plug them into
The original.
the original because we're looking for points on the graph.
Awesome.
So you can plug them in. It doesn't matter if you plug it into this or to the factored form. Sometimes the factored form is a little easier to evaluate with. All right. So let's actually do that here. Remember how to evaluate quickly on your calculator, especially when you've got things like this. Is it going to come up? There we go. All right, so we want to evaluate at a negative 3.7. So I'm going to store that as x, and I'm going to punch in my original function. X to the third plus 5x squared minus 4x minus 20. Okay? So I now know that my max is at 12.6. Okay, so I'm going by 2, so 2, 4, 6, 8, 10, 12. 12.6 is going to be about right there. Okay, so negative 3.7, 12.6 is my max. So now I know my function goes up to here, and now it's going to come back down to here. It's going to go down to my y-intercept, and it's going to keep going at least a little bit. All right, so now I'm going to evaluate my function at 0.37. Okay?
It's negative 25%.
Okay, good. Yeah, if we store that in x, then we can go second entry to get back to where we typed out our original function, negative 20.7. Okay, so now we know that our min is at 0.37, negative 20.7. Okay, so it's a little bit further down. So we go down there, now we go back up, hit our 0, and that is a more accurate sketch of the curve because now we can actually know exactly what those max and min values are.
Mr. Erickson,
Yes.
calculator question.
Yes.
When you did the made x value right there, will that if you're typing in a function, will that make in the y equals whatever?
It won't affect that, no. It's only when you're out on the main.
It's not gonna make it a constant.
No.
And that's the
Because when you're graphing, it automatically continually punches in different values of x to evaluate your function.
Yeah.
Okay? So,
Why are you speaking?
alright, so we've got all that. Should make better sense. Try some practice. Alright, we'll see ya.